Pada tahun 2019, BT2MP memperoleh nilai 100 dari Ombudsman RI terkait kualitas layanan publik sesuai dengan Undang-Undang Nomor 25 Tahun 2009 tentang layanan publik. Oleh karena itu, untuk mempermudah customer mengetahui layanan jasa di BT2MP, kami menyediakan layanan terpadu melalui layanan.bppt.go.id dengan memilih Balai Teknologi Termodinamika Motor dan Propulsi. Di sana customer dapat mengetahui jenis layanan, tarif layanan, serta waktu pelaksanaan untuk uji yang dimaksud. Terima kasih.
BT2MP.
Pusat Teknologi Sistem dan Prasarana Transportasi BPPT berinovasi merancang dan membangun prototipe kereta cepat antar kota berkecepatan 250 km per jam dalam jangka waktu 5 tahun ke depan, dimulai dari tahun 2020, ditargetkan di tahun 2024 akan terwujud prototipe tersebut. Tahap awal untuk membuat kereta cepat adalah clearing teknologi. Clearing teknologi sarana mengacu kepada 5 negara utama yang dipandang memiliki teknologi kereta cepat yang maju, yaitu kereta cepat Jepang seri N700, kereta Cina seri CRH-1A, kereta cepat Prancis seri TGV Duplex, kereta cepat Korea tipe KTX Sancheon, kereta cepat Jerman tipe ICE 3. Hasil clearing teknologi sarana menghasilkan rekomendasi pilihan teknologi yang digunakan sebagai referensi desain kereta api cepat pertama Indonesia. Bentuk muka kepala kereta atau mass of car kereta cepat dirancang sedemikian rupa dengan hambatan aerodinamik kereta paling minimum pada kecepatan tinggi. Untuk mengetahui nilai koefisien hambatan udara bentuk mass of car pada model uji kereta cepat, maka dilakukan uji terowongan angin atau wind tunnel test.
Assalamualaikum warahmatullahi wabarakatuh. Good morning, ladies and gentlemen. First, I would like to warmly welcome His Excellency Mr. Yi Fanping, Science Counselor for the Embassy of People's Republic of China for the Republic of Indonesia. Deputy Chairman of BPPT for Design and Engineering Industrial Technology, Dr. Wahyu Widodo Pandu. Director of Center of Technology for System and Infrastructure of Transportation, Dr. Mulyadi Sinungharjono. All heads of unit in BPPT, speakers, moderators, distinguished guests, and all the audience. Welcome to webinar on propulsion system for high-speed train. This webinar is part of implementation program of the Joint Research Center for High-Speed Railway Technology between BPPT and Southwest Jiaotong University. In today's webinar, there are 6 presenters who will talk about various aspects in propulsion system. Now, Before we begin our webinar, I would like to invite Dr. Wahyu Widodo Pandu to give keynote speech to open this webinar. Please welcome Dr. Wahyu Widodo Pandu.
Thank you very much, Mrs. Moderator, MC. Very good morning for everybody. Please allow me to share a presentation, very short. I hope you can hear my voice very well, and I hope you all see the screen, the presentation on screen. First of all, Assalamualaikum warahmatullahi wabarakatuh. Very good morning, ladies and gentlemen, speakers and distinguished guests. Excellency Mr. Yi Fanping, as the Science Counselor of the Embassy of the People's Republic of China for the Republic of Indonesia, and also my colleague, Director of Center of Technology for System and Infrastructure of Transportation of BPPT, Dr. Mulyadi Sinuharjono, and all colleagues, head of units in BPPT, and also distinguished guests from ministries and agencies in Indonesia, including the PT-KAI and INCA, PT-INCA, and other audiences. First of all, today we gather here on the webinar on the propulsion system for high-speed train. This webinar actually is part of the Joint Research Center for High-Speed Railway Technology between BPPT and Southwest Jiao Tong University to accelerate high-speed train technology acquisition in Asia. BPPT actually following as the government agencies on the assessment and application, or we call it JIRAP, according to the Indonesian law number 11 year of 2019 on the national science and technology. There are 7 BPPT roles, which is number 1, is on the left side is engineering, and as the technology clearing, technology audit, and also TOT, transfer of technology, and we are doing also a technology intermediation with other stakeholders, and science and technology diffusion means that science and technology has to be implemented in the public or in the daily lives of people in Indonesia, and also the technology commercialization. The last one, the number 7. We are responsible for acquiring new technologies, responsible for providing innovation, and push toward the successful of the implementation of the technology. That's the goal of the 7 BPPT roles. And also during the national coordination meeting on the March 2021 this year, directly presidents gave us the instruction, actually 3 instructions, important instruction, that BPPT must, 1, searching for new innovation and technology, and also number 2 is the leading the acquisition of advanced technology to support national economy recovery, and the third one, number 3, become the center of artificial intelligence in Indonesia. So this is the 3 important messages from the President Republik Indonesia, Excellency Mr. Joko Widodo. Ladies and gentlemen, the urgency of the high-speed train technology acquisition. Actually, first of all, that the national railway industry must reduce the dependency to imported components and able to compete in international market. There is quality sensitive issue to enter international high-speed train market. And number three, the air transportation services in Jakarta to Surabaya corridor almost reach its capacity. Always, and it is predicted that full capacity will be happen within a few years. Now, instead of the pandemic season, so during the normal situation, the air transportation Jakarta to Surabaya, for example, is really very crowded. And also multiplier effect of the high-speed train industry in economy and financial aspects. And lastly, the international high-speed train marketing is increasing significantly. And as the National Railway Master Plan, the Ministry of Transportation in 2018 have issued the Master Plan high-speed train from Jakarta to Surabaya. There are also some constraint because the existing railway still narrow gauge, but for the high-speed train, it is required that the railway must be standard gauge 1435 millimeters. So that's the situation. Acquiring the additional track is not easy because we need to do the land acquisition, which is not easy also to along the railway, which has been the develop of the economic area along the track between Jakarta to Surabaya. It's another issue. But also in Sulawesi, we have started with the standard gauge for the railway from the Makassar to Parepare. I think this is going to be the prospect to implement the high-speed train since the railway implemented there already using the standard gauge. The roadmap we are expecting, and in 2020 we have been done the technology clearing and basic design for high-speed train, and this year we are working on the detailed and manufacture design, and starting next year we will continue doing the manufacturing and testing of high-speed train component. Also the following years high-speed train integration and functionality testing, and the last one, finally, hopefully in the 2024, the prototype of Indonesian high-speed train will be tested as a whole system. It is probably quite promising that we hope that we have the prototype for the high-speed train in 2024. But again, it's based on the budget available. Next, the collaboration between BPT and Southwest Jiaotong University in Joint Research Center for High-Speed Railway Technology has already started since 2019, 2 years ago. The objective of this joint research are to carry out scientific and technology collaboration, and also to promote academic exchange between Indonesia and China. Next, to strengthen the scientific and technology competence in Indonesia, and the last, to boost the long-term and stable development of high-speed railway technology between China and Indonesia. program implementation. Various programs has been held as part of the implementation of this joint research center, such as visitation from both sides, webinar series and technical discussion between BPT and Southwest Jiaotong University. Today's webinar is the continuation as the webinar series between both BPT and Southwest Jiaotong University. Today, webinar focus on the topic of the propulsion system of high-speed train. As the propulsion system is a vital component in a high-speed train, therefore the technology acquisition in the field is an important part in the development of high-speed train. Today, we will join the presenters from BPT, Brawijaya University, as well as from the Southwest Jiaotong University to explore 6 topics in this area. We are welcoming for all the speakers and all the audience from there are 6 speakers today. I hope you have a fruitful webinar for today on the topic of the propulsion system for high-speed train. And also, thank you very much for attending this webinar. Diplomatic relationship between the people, Republic of China and Republic of Indonesia has long history of 71 years. We hope that this collaboration can strengthen this relationship and benefit the technology advancement in both countries, Indonesia and China. Thank you very much. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam. Thank you.
Thank you, Dr. Wahyu Widodo Pandu, for keynote speech. Now I would like to invite the Science Counselor for the Embassy of People's Republic of China for the Republic of Indonesia, His Excellency Mr. Yi Fanping, to give an opening speech. Please welcome His Excellency Mr. Yi Fanping.
Thank you. Dear Dr. Wahyu Widodo, Deputy Chairman of BPPT. Dear Dr. Muyadi, Director of PTSPT BPPT. Dear Professor Chen Rong, Vice Dean of Civil Engineering School of Southwest Jiaotong University. Dear professors, experts, ladies and gentlemen. It's my great pleasure to join the webinar between Southwest Jiaotong University and the BPPT. On behalf of the Chinese Embassy in Indonesia, I would like to extend my warmest congratulations to the opening of the webinar. Because my colleague, Mr. Xie Chengsuo, has just transferred to the Chinese mission to ASEAN as science counselor and will focus mainly on science technology international cooperation between China and ASEAN. While my another colleague, Mr. Liu Lei, will take over Mr. Xie's duty to facilitate the cooperation between Southwest Jiaotong University and the BPPT. Since Chinese Ministry of Science and Technology and the Indonesia Ministry of Research, Technology and Higher Education signed the MOU in April 2019, both sides have conducted couples of activities, including joint research, platform construction, training workshop, personnel exchange, academic exchange, seminars with fruitful progress. Although the pandemic is still developing, I'm pretty pleased to see that the cooperation between the two sides has not been affected by the pandemic, but is still continuing to deepen and advance. I would like to express my sincere gratitude to both parties for the joint efforts in co-establishing the China-Indonesia Joint Research Center on High-Speed Railway Technology. Taking this opportunity, I would like to briefly on latest updates of bilateral cooperation between China and Indonesia. After the outbreak of the pandemic, the cooperation between the two countries has not been affected, but has risen against the trend. Two heads of states, President Xi Jinping and President Joko Widodo, have made phone calls and reached important consensus on anti-pandemic cooperation and the economic recovery. The Jakarta-Bandung high-speed railway projects has finished 75% and will be completed in 2022. China and Indonesia vaccine cooperation takes the lead in the world. More than 100 million doses of Chinese vaccine will arrive in Indonesia until the end of this month. We believe that Chinese vaccine will be helpful for Indonesia overcome the pandemic and help Indonesia resume economic recovery. Finally, I hope that both parties will continue to conduct concrete cooperation activities, especially in capacity building and research and joint research under the pandemic. The embassy is ready to facilitate the cooperation between Southwest Jiaotong University and the BBTT at any time. We wish this webinar a great success. Thank you very much.
Thank you, Mr. Ivan Fink, for the opening speech. Now, before we begin the presentation session, we would like to take a photo to commemorate this webinar. Therefore, I would like to ask all the participants to open the video so we can take the photo.
MC, saya nggak bisa menyalakan video. Okay. Yeah.
We have 4 pages of photos, so we will start with the first page. Second page.
Hi, Lita. I think we can share the screen and we can take photo together. Is that okay?
Sorry, can you?
I mean, you can share the screen for everyone, and we will take the photo together. Okay. 他们都可。Because we can only see you in on the monitor.
Okay.
Okay, we got it. 我们要不然一起站过来，这样子是好一些。OK， 站过去。对，小乐你就在那。哦，这样子。对，这样子，我们这样子。对，就不站在这儿打了，我们就往这边来吧。对，一起，对，没问题。后边主要好，这样后边哈，你们一起的。你要往那边，在那边。肖老师往这边来，对，主要是把后边那个 list 那个。好。Okay, we got the picture. Thank you very much.
Thank you.
So,
shall we start the conference?
Yes, I will introduce the moderator.
Okay.
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 Thank you, ladies and gentlemen. Now, without further ado, we will start our presentation session. The presentation session will be divided into two sessions. The first one will be the speaker from Indonesia. This first session will be guided by Mr. Benny Halvina from BPPT as the moderator. Now I will pass the baton to you, Mr. Benny. Mr. Benny, you can start now.
Okay, thank you, Ms. Lita. Assalamualaikum warahmatullahi wabarakatuh. Good morning, everyone. Our Honorable Deputy for Design and Engineering Industrial Technology, Dr. Wahyu Widodo Pandu, Honorable Director of Center of Technology for System and Infrastructure of Transportation, Dr. Mulyadi Sinung, His Excellency Mr. Van Ping, Science Counselor, People Republic of China, Embassy in Indonesia, distinguished speakers and guests, and all participants from university and also from railway industries. Today we have hundreds participants. It's very great. And we would like to welcome all of you. And thank you for joining us today in the webinar transportation series, Propulsion System for High-Speed Train. My name is Benny. I'm from the Center of Technology for System and Infrastructure of Transportation. I will be your moderator today, and allow me to guide you through the webinar session to get fruitful discussion and benefit for both countries. So as mentioned by Mr. Deputy, this webinar is part of the collaboration between PPPT and Southwest Jiatong University in the field of high-speed train, with its main focus is the propulsion system of the train. So the objective of this webinar today is to give overview and insight of the technology development in the propulsion system, and also as the scientific sharing platform and collaboration between Indonesia and China. Therefore, we expect it to have further discussion related to the propulsion system and also research collaboration between Indonesia and China. So one of the vital components in railway is the propulsion system. It allows the train to move in desired speed and performance. Therefore, the knowledge related to propulsion system is significant for national railway in Indonesia to support the National Railway Master Plan 2030. So it's also an interesting fact that this month, June, is also coincide with the commemoration of the 10 years high-speed rail operation between Beijing and Shanghai. So we hope that we can get a share of knowledge from our colleague in China to improve our industry. So without further ado, let's begin the presentation session. The first speakers to open the session is Mr. Nachep Suryana from the Center for Thermodynamic Motor and Propulsion Technology, PPPT. Mr. Nachep will talk about the propulsion laboratory for train testing. Mr. Nachep, you will have 20 minutes to deliver your presentation, and I will give 5 minutes remainder in the end of the session. So, Mr. Nachep, the time is yours. Thank you.
Okay. Thank you, Mr. Benny. In the next 20 minutes, we'll talk about propulsion laboratory, especially that right now is tried to be developed in PT2MP. Allow me to share screen. Okay, Propulsion Laboratory for Train Testing. I'm Najib Suryana from Laboratory for Thermodynamic Motor and Propulsion, the BT2MP BBPT. I'm a testing engineer. So BT2MP is actually the Center for Thermodynamic Motor and Propulsion Technology. It is government body which has tasked to carry out technology services in the areas thermodynamic, motor, and propulsion. BT2MP right now is capable of testing motor, both internal combustion engine and electrical motor. Traction motor testing facilities is under developing right now, but still currently use same facilities as IC engine testing facilities. So this propulsion laboratory is actually needed in order to support the national rail industry. So for testing standard in the propulsion system or motor traction can be carried out using standard. This is standard IEC 60349-2, section 2. This is electric traction rotating electrical machine for rail and road vehicle. So the standard is actually not only for railway application, but also for road vehicle. So part 2 is electronic converter fed alternating current motor. BT2MP basically is capable of testing electrical motor with maximum voltage 480 volt. But for traction motors with voltage greater than 480 volt is in development phase. Standard is we can use also standard IEC 61377 part 2. Yeah, this is railway application rolling stock combined test method for traction system. This standard is more comprehensive, yeah, than the first standard, because first standard actually this is like component testing, yeah, test only traction motors. Okay, the IEC 603.49 part 2, the objective of the standard is actually to enable the performance of a motor to be confirmed by tests and to provide basis assessment of its suitability for a specified duty or for comparison with other motors. This standard is applied not only for train, but also train traction, but also for car traction system. This standard tests only this standard tests only electrical motors, include with its converter or inverter, and can be categorized as a component testing. More comprehensive testing testing may be used combined test method, IEC 61377 part 2. There are 3 test categories in this standard: type test, routine test, and investigation test. So in this presentation, I will talk only maybe a type test, where this test consists of 4 parts. So temperature rise test, characteristic test, upper speed test, and vibration test. Let me talk first about main component for testing motor traction. So for testing traction motor, we need the following components. Firstly, load unit. So in our laboratory, we use the dynamometer, electrical dynamometer. We have also eddy current dynamometer, with stable power curve. And secondly, maybe we need universal inverter. This inverter is needed when traction motor does not have inverter with it. Yeah? In IEC 60349, it is recommended that motor to be tested is included with its inverter, but sometimes it is not available, yeah, the inverter. So secondly, instrumentation, we need power meter, sensor, milliometer, sometimes megger test equipment to test the insulation of the motors, and also data acquisition system equipped with software that capable of controlling major equipment. Yeah. Because in this case, load unit must be controlled. Yeah. Also, we need maybe torque meters. If we use direct measurement method for power measurement, so the power is measured directly from shaft. So we need torque meter in this case. But for testing electrical traction, we can also use other methods, yeah, by measuring current and voltage generated in the load unit. So we can calculate also the power of the testing motor traction, tested motor traction. So this is a schematic diagram. So the motor under tested is connected through shaft with AC or DC dynamometer, or maybe eddy current dynamometer, and yeah, this is controlled by computer automated system. Yeah. So this is the dynamometer act as load unit, and in our lab, so the torque meter is installed in the shaft here. So direct measurement, we use direct measurement method for measuring the power of motor traction. So this is just one example. This is one of the electrical motor. This is not a traction motor, sorry. It's just how to prepare electric traction motor testing. This is just one example of connecting between the motor under tested with the dynamometer using shaft, yeah, joint without any other damping equipment. Yeah, so direct connect to the dynamometer. Oh, this is one of BT2MP existing testing facilities. This is engine test cell number 7. Yeah, we have AC dynamometer here. Can absorb power up to 750 kilowatt at 4,000 RPM, and it has also maximum torque up to 4,200 Newton meter. We have also another test bed, yeah, with various capacities. We have also engine test bed number 8, has a maximum capacity of 440 kilowatt. Speed is very similar, and it has also maximum torque about 2,400 Newton meters. We have also test cell number 6. It has a capacity of 150 kilowatt. This kind of, the engine test cell number 6, it use eddy current dynamometer to act as load equipment. Yeah. And we have also small engine test bed with capacity of 30 kilowatt using DC dynamometer. So this is one engine test cell 8, but in this test stand, this is IC engine. Yeah? As I said, this laboratory actually designed originally for IC engine testing facilities, not for electrical. But in principle, the load unit can use also for electric traction testing. Okay, this is one of type tests in standard ICE 60349 part 2. Yeah, this is temperature rise test. So the motor should be tested at rating. So for example, if the traction motor has 200 kilowatts, so the motor should test at 200 kilowatt, and some part of the motor must not exceed the temperature. This is number in Kelvin, 130 for class B thermal class insulation system, 155 Kelvin. So above air temperature or the cooling air in the test bed, yeah. So must not exceed this temperature when the motor is running at the rating power. Yeah. So for totally enclosed motors, the limit here must be increased by 10 Kelvin. So this is some limit in the Sutter winding, rotating field winding of synchronous motors. So the method of measurement must be use a resistant thermometer detector, yeah, RTD or PRT. And sibling also we measured and damping winding. Okay, a characteristic test. This is second test in ICE 60349 standard. So the purpose of the test is to demonstrate compliance with the specific characteristic shall be carried out by measuring the electrical input to the motors and mechanical output from it. Yeah. So we compare. So we can measure the efficiencies of the efficiency of the traction motors by knowing the input power and the output power from the motors. So the output measured in our lab is directly from sub using torque meter. So and dynamometer used as a power absorber. So the output is measured directly from tolerance of the traction motor declared torque at any electrical input in the specified characteristic between the values corresponding to the maximum torque and to 90% of the maximum speed shall not be less than 95% of specified values. So if minimum 95% or more, so it's we can say the motor is okay. Yeah. So and then upper speed test, yeah, an upper speed type test shall be carried out on all type of converter fed motors. In this test, motors should be run for 2 minutes when condition is hot at 1.2 times the maximum working speed. Yeah. Highest rotational speed assigned to the motor by the manufacturer. So 20% above the maximum working speed, yeah, for the opposite jet. And then measurements shall be taken before and after the test to determine the extent of any distortion of the rotor. So the last one is vibration test. So qualitative vibration measurement is taken at machine or motor only, gearbox not included there. For vibration measurement during type test, the machine can simply be placed on the test board without any mounting equipment. So the velocity of vibration at machine speed up to 3,600 or 3,600 revolution or RPM, yeah, shall be within the limit of 3.5 millimeter per second. And for speed above 3,600 RPM, the velocity shall be less than 5.25 millimeter per second. So this is a criteria for passing the vibration test. So note the type test shall be properly carried out using the converter to be employed in service. If the motor...
Mr. Najib, you have
Okay.
5 more minutes.
Yeah, thank you. But as an alternative, a supply which closely resembles the supplies from the vehicle converter in waveform and harmonic may be employed. So therefore, BT2MP must be equipped with general inverter. Yeah. So the current situation in our laboratory with the existing facilities, BT2MP basically capable of testing traction motor using standard IEC 60349 part 2. Yeah. So major drawback in current situation are BT2MP does not have step-up transformer yet for motor traction that has voltage greater than 480 volt. High power display does not exist now. Also, originally, all test bed in BT2MP designed for testing internal combustion, or IC engine, yeah? Diesel engine, gasoline engine, like that. So to use for testing electrical motor traction, some modification has to be made. So this is the second standard, IEC 61371 part 2. Yeah? This testing method more comprehensive than IEC 60349. The combined test gives the opportunity to run the component of the traction system under test with operating condition close to service. So this is the difference with 60349. This standard applies to traction system consists when it applies of traction motor, converter, traction control equipment, including software, transformer, input filter, brake resistor, main circuit breaker, cooling equipment, transducer, contactor, etc. So the tests this standard are classified so as mandatory tests and optional tests, yeah, which consists of 24 tests. So we can see in the table A. So this is 24 tests in combined tests, but mostly this is optional tests. Only 8 of them is mandatory tests. Yeah. So if we see from this list, so we can see that testing item from the standard is actually close to standard IEC 60349. Yeah, just like torque characteristic test at motor hot, torque characteristic test at motor cold. Also, we have here temperaturized test at a constant load. Also, temperaturized on root profile. Yeah, so root means in this standard, root must be represent the real operation of the train. Yeah. So also we have motoring, braking, transition, vibration also of line. Variation of line voltage, sudden loss of regenerative braking capability, regeneration capability. Yeah. Also commutation test only for DC motor. So this is overview of traction system architecture of the standard. Yeah. Note on the standard, some of the mandatory tests in the standard is very similar to type test in IEC 603.9, torque characteristic, temperaturized test, but the standard use duty cycle which mimic operating condition close to service. So duty is actually defined as a load to which the traction system is subjected, including motoring, coasting, yeah, when, for example, the rail is a little bit down, yeah, electrical braking. So what is duty cycle here? Duty cycle specified sequence of operation condition, yeah, the speed and torque over time on an elementary road. So this elementary road means for mainline train, for example, this is road between two cities back and forth. So in tramway, for example, this is route between two stops. In metro train, for example, this is route between two stations. Yeah. So that is duty cycle or route. Yeah. Okay. The time is up. Sorry. Maybe. So this is typical test cycle. Yeah. This is just an example. Torque characteristic for testing torque characteristic of traction system at constant speed. Yeah. Here is speed, and this is the torque, and this is voltage. Yeah. Applied. This is DC input current, DC input voltage, and this is the torque output there. So this is one example of cycle test. Yeah, how to use in this figure. We see the tests include acceleration and braking. Here is the braking, yeah, and constant load, and etc. So those who interested in the combined test can read the following paper. This is from Southwest Jiaotong University. Yeah, I think Mr. Xing Jiangdong is lecturer in School of Electrical Engineering in Southwest Jiaotong University, Chengdu. The performance study of combined test rig for metro train traction. Okay, that's it. My presentation. Thank you for your attention. The time. Back to Mr. Benny.
Okay, thank you very much, Mr. Najab. Very interesting presentation about the capability of the BPPT to perform the tests of the traction motor. So information for the audience, we will proceed to the presenter until finish, and then after that we will have a panel discussion and followed by the question and answer. So moving on to second agenda today, we have Mr. Diploma Engineer Muhammad Rusli from Brawijaya University. He's an associate professor at the Brawijaya University with a background education from ITS Surabaya and Technische Universität Braunschweig, Germany, and finishing his master at the University of Wollongong, Australia, and also the Department of Mechanical Engineering, Faculty of Engineering, Brawijaya University. And Mr. Muhammad Rusli will be talking about the control system for high-speed train. So without further ado, please welcome Mr. Muhammad Rusli from Brawijaya University. The time is yours, Mr. Rusli.
Okay. Thank you. Assalamualaikum warahmatullahi wabarakatuh. Good morning, ladies and gentlemen. Thank you, Mr. Benny. You can see me? Hello? You can see me?
Yes.
Okay.
Yes.
Thank you, Mr. Benny, for the time. And I am Muhammad Rusli from Brawijaya University, now as a member of the control laboratory in Brawijaya University. Last time in 2012 and 2013, I have been member in the power electronic laboratory and mechatronic laboratory in the University of Wollongong, Australia. There. And then just and in universities of Wollongong, actually, we have developed the vector control with considering harmonic and vibration. One of the approach to reduce the effect of the solvent using the solvent observer and QFT, quantitative feedback theory. This is for me. This for 2 years there, And then now I want to share my slide. So actually, I just only this Indian's presentation. I would like to present about the additional controller in vector control, because I think the vector control algorithm is popular. I don't need to present today. Just only I want to present the disturbance of circle or anti-slip realization control for high-speed train. Because this is similar with I have developed in Australia in University of Wollongong, but in Australia I implemented the algorithm to the machine too, not in high-speed stream. This is problem. But I think I can extend, I can develop for the high-speed stream. And this is the all electric laboratory in Wollongong. Just I have done this. I have done developing control algorithm there for the.
Excuse me, Mr. Rusli,
Yeah.
could you please display the presentation to full screen?
Okay. Okay. I'm sorry. Sorry. Like that. Moment. Like that.
Thank you.
Okay. Thank you. This second picture is actually the screen. You know, we can look the result of the algorithm in inverter. And okay, I think why I will talk about anti-slip, because Indonesia is a country with high rainfall, and the level of gas in the air and the level of humidity is relatively high. So this gives rise to the phenomenon of slip between the hills and the track getting bigger. They can cause decrease in the coefficient of friction between the hills of the train and the rail. The kind of phenomenon can cause discomfort for train passenger and can accelerate the weight of rails and train. Therefore, the propulsion system of high-speed train in Indonesia should be give attention for the anti-slip readaptive control. Actually, the readaptive control have been done in the world. Have been done, and success can reduce the slip. But in the paper, I have read paper. This paper is not give attention the variation of parameter of system. So I think I propose in the high-speed strain here, I will propose the algorithm control anti-slip with considering variation of parameter. The slip phenomenon is caused actually by decrease in the tangential force. This tangential force is main problem of the train. What is the tangential force? This force is strongly influenced by the coefficient of tangential friction. The tangential friction affected the tangential force. This factor is greatly influenced by the level of wetness and dust in the room. The use of the slip algorithm is proven, it's already done, to reduce the slip effect, but the vibration of the high slip bogey has affected the estimation of force friction coefficient, so that it can cause the anti-slip factor value does not match to the reality, and fluctuation of the motion system parameters has also affected the estimation result. Therefore, high-speed train, I think, in Indonesia requires modification of free additive control by the disturbance observer with considering the vibration of bogey and the variation of parameters. And then this is sorry. There's no I'm sorry. Before I present before I give the presentation about before I talk about the anti-slip control, I will take little bit over voltage control, because in the high speed, the voltage in motor, the traction motor is very high, and the current also very high, and also the regenerative current as the braking mode is so very high. So that's why I think we have to also develop the over voltage controller. It means if the voltage in the capacitor more than 2000 volt, we have to reduce. We have to choose, because the over voltage can damage the power system. This is the algorithm for the over voltage control. This is the reference. This is reference. Voltage reference compared with the voltage in the capacitor. If the bigger the V reference or V capacitor bigger than the V reference, the result is negative. So negative will force the PI controller and then will reduce the voltage in the capacitor. This is can protect the power system from the failure system. Okay, now I will talk the anti-slip controller. Actually, the concept anti-slip controller is from the board here, because the question is actually how to know the force, how we know the tangential force. Because if we measure the tangential force, because their axis the vibration very high, so can influence the measurement result. So that's why we have to estimate, not the direct measure, not measure directly the variable, but we have to estimate this. From the equation, we can know that the estimated real load torque of motor can be calculated, can be predicted by the torque of motor and the frequency of motor. From the both equation is the principal key of the anti-slip controller. So, and the tangential force is depend on the real load torque model. And the tangential force, if you see curve in the right side here, the tangential force is depend on strongly on the slip velocity. If slip velocity is 0, the tangential force coefficient is maximum, it means the slip is the tangential force is very, very big. So that's why how actually the goal of the anti-slip or the readditive control, how to make the torque always in the maximum tangential force coefficient, so that we can have an velocity slip is 0. If the velocity is 0, there's no slip in the hill. Then when the hill torque, the high speed train exceed the maximum tangential force, the high speed train has the slip phenomenon caused by the excess of torque. Therefore, the readdition control system should control the motor torque to adherent. Then The question is how to get the maximum force coefficient. With estimation tangle force per azimuthal torque, it can be done. The disturbance azimuthal can be found easily and precisely. Actually, the disturbance azimuthal I have done in the Australia, but for machine tool. Maybe I think it is suitable also for the high-speed train. How to the equation actually, the following equation, how to put the algorithm distribution azimuthal in machine tool can be used in the high-speed train. That is this problem. And the student also find the principle like that. So the result of principle observation go to come into the top command. Mean the disturbance observer, the output disturbance observer influence the determinant of top command. If the temperature force azimuthal is very big, so the top command should be reduced. This is only the principle according to the diagram. And then the second thing, in high-speed train, normally sometimes using an sensor with the resolution is very low. So sometimes, if the mission variable is very low, because it's a long time during the mission, this is problem. So better in high-speed train should be use sensor-less vector control system. Without sensor, we can estimate from the variable speed and current of the motor. We can estimate the magnetizing current and estimate on the transformation force, and then estimate and load torque. I think better sensorless because I think the vibration of the high-speed train is very, very big. Okay, this is the curve for the anti-slip. For the process, if the high-speed train is in the acceleration mode, the motor torque is controlled as shown in figure A. Is accelerate mode like that. Accelerate mode. The motor torque is controlled if the slip detection is exists. Slip detection rise, so we have today from the curve, the left side. The left side is also for acceleration, the right side for braking mode. This is anti-slip, this is anti-skid. This is different, but the difference only is negative, this is positive. If the torque command, the torque motor is accelerate and then meet a slip detection, torque command should be decreased until the slip is in the certainty value constant, and then keep constant, and then the increase in the torque command, and if meet again the slip detection, keep constant, and so on. There is the curve, the motor torque control action is figure B. The additional control is okay. Okay, this is the algorithm, the simple, the concept algorithm relative control. If the slip skid phenomenon is detected, the motor torque is reduced to the torque limit, which is based on the estimation tangent force, and kept on during time T1 in order to reach other. Okay, so until this, if the tangent force is, I think the torque load is depend on the estimated tangential force. The motor torque is recovered to.
Mr. Rusli, you have 5 minutes.
5 minutes, okay, thank you. Which is based on the estimated tangential force.
The motor torque is kept on during time T2 and increasing gradually until the rejection of the phenomenon. Experiment result. This is in Wollongong, just for machine 2. I think this is I can implement it in high speed train because the algorithm using the vector control in distributed observer with Kalman filter here, and then also this we can see this oscilloscope picture. That this is the vibration. You can see in the velocity. You can see the vibration, and then the result after implementation of the algorithm control, the vibration reduced. The vibration effect can be reduced by the stopper observer with KFT actually, not only because here I also gave attention for the variation of parameter, because as the motor run, the parameter of motor will be varied. Okay? Then we cannot calculate the controller if the parameter of motor is varied. Okay, this is, and this is the from the print. I have printed it. This is the left side is with vibration. The velocity with vibration. This is the wrong statement. And the right side is actually after implement the vibration algorithm control with Kalman, with KFT, the vibration can be reduced like the right side. Okay. Conclusion: the anti-slip radiation control based on the visible observer, considering first resonant frequency result point out that the proposed control method has desired anti-slip radiation control response. The proposed dissolvent observer is effective to reduce the vibration of the estimated force, and the tangle force utilization ratio can be high. This is also I have done in University of Wollongong with the algorithm, the similar algorithm in high-speed train. Thank you very much for the attention. Assalamualaikum warahmatullahi wabarakatuh.
Thank you very much, Mr. Rusli. An interesting topic about the control usage to avoid the slip and skid in the railway. So now we move to the third speakers today. It's from Brawijaya University. Mr. Waru Juriatno, STMT, is a member of IEEE, received the bachelor degree and master degree in electrical engineering from Universitas Brawijaya Malang and Universitas Gadjah Mada Yogyakarta, Indonesia in 1995 and 2006, respectively. Currently, he is a lecturer with the Electrical Engineering Department, the Brawijaya University Malang, Indonesia, and his research interests include medium to high voltage electronic device, the electronic vehicle motor converter, and embedded system. So without further ado, let's invite Mr. Waru to deliver the presentation. Mr. Waru, the time is yours, 20 minutes from now.
Okay, thank you, Mas Benny, as a moderator. Thank you for the opportunity for me to deliver this presentation. Okay, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Good morning, ladies and gentlemen, and may God bless you all. Thank you for the opportunity for me to deliver what I've done during latest weeks and months regarding the developing of the motor drive for the high-speed train application. Okay, I hope you can hear my voice clearly. And to conserve the time, I will share my screen to show my presentation. Please allow me to do this.
Okay, Mr. Waru, please share your screen.
Okay, just a minute. Okay, have you seen the screen?
Yes.
Okay. Okay, I will give the result from my brief literature review. Yeah. So this is only the result of my literature review regarding the SiC, silicon carbide power devices in medium voltage and high power application. Okay. Why we attract to these silicon carbide devices? Although the silicon carbide or IC devices has been developed dates back to the 1980, its emergence just started appearing in about 2001. Why SiC or silicon carbide devices become more attractive? We can see if we compare the silicon-based device characteristic compared to the silicon carbide-based devices characteristic, you can see in this graph. This graph shows intuitively how the silicon-based device compared to silicon carbide and gallium nitride device, which we call the silicon carbide and gallium nitride device as a wide bandgap power devices. We name it wide bandgap based on the bandgap characteristic of this material, this silicon carbide and gallium nitride material. Okay, due to wide bandgap material, they have the characteristic, special characteristic, especially in the SiC. SiC have the thermal conductivity larger than silicon-based material devices. It's more than 2 times higher thermal conductivity, and the breakdown field, we can see in this graph the breakdown field of the SiC devices far more than 4 times than the value of breakdown field of the silicon-based power devices. That's why the silicon carbide devices fits to the medium to high voltage application, which need breakdown field in million voltage per centimeter range value. Okay, this graphic show us the advantage of the silicon carbide or generally wide band gap power devices compared to the silicon devices. The higher thermal conductivity enable us to make smaller devices and smaller thermal handling component, so we can build equipment with a smaller dimension, less dimension and less weight, which can reduce the dimension and weight of the equipment that will be used in the mobile I mean here in the vehicle application. So we can see in this table the quantitatively the difference of silicon carbide and the silicon material. We can see here the critical field or breakdown voltage. Breakdown field here is Si or silicon-based device have the critical field value only 0.3 or around 300 kilovolt per centimeter, while the silicon carbide material have the breakdown field 3.5 megavolt per centimeter. It's almost 10 times higher than the silicon power devices. And so we can see here the thermal conductivity of the silicon carbide power devices almost more than 3 times than thermal conductivity of the silicon device. And the other parameters, especially the electromobility, which will determine the conductivity of the material. The silicon have a better mobility, electromobility compared to silicon carbide, and also gallium nitride. But due to the higher critical field of the silicon carbide, we can make a smaller device using silicon carbide, and so the conductivity will become relatively similar to the conductivity of the silicon power devices. Okay, this is the conclusion of the comparison of the silicon carbide and silicon device property. You can see here the breakdown field 10 times higher. The silicon carbide has breakdown field 10 times higher than silicon, and the epitaxial layers can be built 10 to 20 times thinner, more than the silicon counterpart. And also it has a higher thermal conductivity and higher band gap. So it can give the advantage of the silicon carbide devices compared to silicon. Breakdown field give a result in lower on-state voltage drop, while the thinner epitaxial layer will produce the faster switching speeds, theoretically 100 to 1,000 times than silicon counterparts. And also the higher thermal conductivity make the silicon carbide devices able to handle higher chip temperatures, while the silicon devices usually work until the temperature 125 degrees Celsius. The silicon carbide devices able to work normally until the temperature 250 until 300 degrees Celsius, or until 3 times higher than silicon counterpart. And due to higher band gap, the leakage currents on the silicon carbide devices quite low compared to the silicon counterparts. Okay, this is graphically show the performance comparison of the silicon carbide MOSFET to the silicon-based IGBT, which silicon IGBT is the most popular device in the power electronic today. Most motor drive converter use silicon-based IGBT as a main switching component. So we can compare the performance of the silicon carbide MOSFET and the silicon-based IGBT. The first, we can compare the collector emitter voltage on the IGBT, silicon-based IGBT, compared to VDS or drain source voltage on the MOSFET, SiC, silicon carbide MOSFET. You can see here in the low current under 20 amps, the value voltage collector emitter voltage on the IGBT and the drain source voltage of the MOSFET relatively similar. But for the higher current, higher than 20, the MOSFET drain source voltage become higher compared to the collector emitter voltage of the IGBT for the same current value. For example, here in the 80 ampere current, the collector emitter voltage in the IGBT will be around 3 point something here, while the drain source voltage of the MOSFET, SiC MOSFET, will be 8 point something volts here. So at the 80 amps current, the MOSFET drain source voltage become far more higher than the IGBT collector emitter voltage. Of course, it affects the power dissipation of the device and also the loss power of the device. So this first graphic shows the disadvantage of the SiC MOSFET, but the second graphics here shows the advantage of the SiC MOSFET. As we can see here, this second graphic shows the turn-off transient curve. We can see here the all SiC, all silicon carbide switch. So this is in the combination of some switching switch device.
Waru,
yes.
5 minutes remaining.
Okay. Okay, let me make it fast. So from the second graphic, we can see the silicon carbide devices give us the fast, very fast turn off transient, and also as shown in the third graph, the SiC MOSFET can operate in the very higher frequency, 2 times than silicon IGBT counterpart. The SiC MOSFET says here can operate until 120 kilohertz switching frequency, while the IGBT limited to this 60 kilohertz. More than this, the IGBT will give significant loss, switching losses. So to be straight, the SiC or silicon carbide devices give us the advantage, especially in the medium voltage and high power application, where the high speed switching of the silicon carbide devices gives some advantage, but also the high speed switching give us some challenge. The first challenge appears at the component level, where the high-speed switching will give us the current overshoot, ringing, and electromagnetic interference, and also switching loss. So this is the first challenge of the silicon carbide application. This challenge appear on the component level. So we can see here the higher the switching frequency, the higher the electromagnetic interference due to harmonics resulted from the component. And also there's a correlation between electromagnetic interference and the switching loss. The higher the switching loss, the higher the switching, the higher the switching speed, switching loss is decreased, but the electromagnetic interference will arise. So in the designing the silicon carbide power devices application as a switch, we must make a trade-off between EMI and the switching loss. The second challenge is the crosstalk effect on the gate driver circuit, because in the bridge topology, the gate of the high side and the low side will cross-talking. So the gate signal on the high side switch will affect on the gate of the low side device. So we must be take care on this challenge. And also the gate circuit will issue the loop in this circuit, and this loop equivalent circuit will give a ringing during turn on and also turn off of the device.
Sorry, Mr. Waro, we have reached 20 minutes.
Okay, I will
your presentation.
Yeah, okay, I'll read the conclusion of my literature review. My conclusion is the fast switching SiC device offers significant advantages in terms of system efficiency and power density over its silicon device counterparts, especially in the medium voltage and high power applications. And fast switching and high DVGT, or the voltage increase ability of SiC will issue some challenge, but the challenge of the fast switching and high DVGT can be compromised using the additional component or adjust or early new topology and using active circuit to control the gate signal. So, okay, thank you for the attention. That's all the result of my literature review. I will give back the screen to the moderator. Thank you very much.
Okay, thank you very much, Mr. Waru. Unfortunately, the time is very limited to provide time for the other speakers. And for the audience, I have some announcements for if you have any questions or you have something to clarify to the speakers, please go right at the chat at the Zoom. And also for you who is joining from YouTube, you can write the question at the comment section. So for the attendance link and the certificate of the presentation will be provided after the discussion is finished. So I hope you keep following us for the webinar session today. And now, since the presentation session from Indonesian side already finished, we will moving on to the session by our colleague in Southwest Jiaotong University. there will be 3 speakers. So the first speakers today is Mr. Xin Zhao, Dr. Xin Zhao. Dr. Xin Zhao is an associate professor of Southwest Jiaotong University. He is also director of Institute for Wheel-Rail Interaction and Vibration and Noise in the State Key Laboratory of Traction Power at Southwest Jiaotong University, Chengdu, China. He is a member of the Committee of International Conference on Contact Mechanics and Wear of Rail and Wheel Systems. He received his MS in Vehicle Application Engineering from Southwest Jiaotong University and his PhD in 2012 from Delft University of Technology, the Netherlands. His research focuses on the dynamic or the transient wheel-rail rolling contact, high-frequency vehicle-track interaction, and mostly targeted at the RCF failures of wheels and rails. So today, Dr. Zhao will be presenting the wheel-rail interaction at high speed topic. So we would like to invite Dr. Zhao to deliver your speech. Please, the time is yours. It's 20 minutes. And I will give reminder 5 time remaining time. Thank you.
Thank you very much for your kind introduction, Mr. Chairman. I would like to, it's my great honor to attend this international meeting to share our discussions and knowledges with our colleagues from Indonesia. With the moment, I will share our screen and yeah. Now, can you see my screen? Yeah. If good, I will start with my presentation. The title of my presentation is Wheel-Rail Interaction at High Speed. So I'm from State Key Laboratory of Traction Power at the Southwest Jiaotong University. This presentation is composed of 4 parts, as you can see from the content. First, a very brief introduction to the high-speed wheels and rails in China. The first characteristic of a wheel-rail system is the profiles. These profiles plays the most fundamental importance in the whole high-speed railway system. As you can see, this is an overview of the high-speed railroad system. If you see closer, you see the very complicated geometry between the wheel and the rail. And at a longitudinal section, you can see the wheel geometry and the rail geometries. One important thing is the wheel is not a simple cylinder, but a coned profile. This coned profile is designed for curving behavior. This we can see from this short animation. As you can see, is a coned wheel set and the wheel set with the cylinder wheels. So when the wheel is a cylinder, you can see it cannot pass the curves. And with coned wheels, the wheel set will pass the curves nicely. So that's why the wheel has a coned profile, but it also causes a problem hunting on the straight lines. That's a drawback. For curving, the mechanism is the wheel set can move laterally, and the wheel radius is different on the left and the right wheels. On the high rail side, the radius is higher, so the wheel can move longer and corresponding to the longer rails on the outside rail. That's why it can cross the curves. But clearly, you need the wheel set has a lateral clearance with the rails, as indicated in the figure. And the flange on the in the inner side of the wheel is the last obstacle to ensure the safety of the wheel set. And this is very important for turnout passing and the short curves passing. And on our side, the wheel set is significantly tapered. And this is specially designed for turnout passing. So in a word, the wheel rail geometry is quite complicated, and every part is designed with a specific purpose. And in history, this development was actually involved empirically, and our understanding is after the engineering. Because of the complicated geometry, so we defined nominal radius, nominal track gauges as indicated in this figure. So the radius at a position which is 70 millimeter aside the backside of a wheel is the nominal wheel radius. And the nominal track gauge is defined at a position below the top of the rail, 16 millimeters. The one high-speed wheel profiles used in China is S1002 CN, which was originally from S1002 in Europe. And during the operation in China, severe hollow wear was observed on the wheels and causing significant hunting problems. And in order to solve these problems, we tried to improve the wheel profile in 2016 and solved the hollow wear and the hunting problem. And you can see from the left below the figure. So the new designed profile LMB10 has a thinner flange with respect to the original S1002 CN. And nowadays, the LMB1 is become a standard profile in the latest generation of high-speed wheels, high-speed trains in China. And another wheel profile used widely in China is LMA here, you can see. And this profile was developed in 1990s by China Railway Rolling Stock Corporation. And this profile was mostly used on wheels with a radius of 860 meters. And in combination with the wheels, the rail profiles are mainly CHN60 and 60N are used in China. And from the right side picture, you can see the 60N with the respect 60 was flattened at the two gauge corners. And this methodology was designed to avoid the rail gauge corner rolling content fatigue. And this a second important phenomena with respect to wheel rail is the rolling and sliding phenomena. Here, if we assume the wheel and the rails are rigid bodies, and you can imagine the contact point at O will be the instant center of the wheel, and where the speed is 0. And in reality, the elasticity is present, but the speed at the contact point O is still very low due to the high stiffness of wheel rail materials and the resulting small strings. This is why the train can reach a very high speed. But it has also drawbacks and causing difficulties. The high stiffness of wheel rail material results in very small content area, small strings, high stress, and large gradients. With respect to the tie rod contact, where the content area was typically over 70,000 square millimeters, and the maximum pressure is less than 2 megapascal. But for wheel rail content pads, the area is just about 150 millimeter square, and the maximum pressure is over 1 gigapascal. So, because of this much smaller content area at much higher stress levels, a lot of technologies which can be used in studies on road contact. For example, the transparent rod used in the pictures I show in the slider. With this transparent rod, you can observe what happens in the contact pads. But these similar technologies are not possible on the wheel rail contact due to the very high pressure levels. Because of this fact, so nowadays, no technologies is available to measure the content area and the stress distribution inside the content area. That's why most of the studies on wheel rail contact mainly depend on the theories and the simulations. In practice, there are also some measurement, for example, instrumented wheel set or instrumented track, which can use to measure the dynamic content forces on board or on trackside. But for this kind of systems, the calibration are usually conducted in statics or at a very low speed. So this limits its application at high speed. Another drawback is high sensitivity to contact surface irregularities. For example, the shuttle wave irregularities we are concerning in daily running are typically those with amplitude above just 50 microns. And from this results shown in the slide, you can see the dynamic content force excited by wheel polygons with an amplitude just 0.2 millimeter, but it results the dynamic content force doubled. So the static load is about 70, and the maximum dynamic load is over 140. So this high sensitivity is coming from the high stiffness of the wheel rail materials. And this is the drawback related to the wheel rail system. And another phenomena being very important in traction, braking, and curving is the rolling sliding phenomena and the resulting creep phenomena. From this diagram, we can see the rotating wheel above the rail. And at the contact point O, there's a circumferential speed, omega times r. And there's also a forward speed, v. At O, these two speeds are in the reverse direction. So you can imagine if v is equal to omega r, then the delta v, so the difference between these two velocities will be 0. And then the wheel is on the purely rolling on the rail. And no friction force is transmitted through the contact area. And the creepage, which was defined by the delta v divided v, is 0. And this, in this case, the wheel moves forward the same, the distance moved forward in one cycle is the same as the circumference of the rail of the wheel, as indicated in the picture below. If the two velocity are different, and the wheel will be in braking or traction, and as indicated in these two equations. So in this case, the wheel will rolling and sliding at the same time over the rail, and the two different directions means if the v is greater than omega r means braking, and if it's less than omega r means traction.
Excuse me, Dr. Zhao, you have 5 minutes left.
Okay. If we see the stick and this rolling sliding will result in adhesion slip detection, and besides outside the contact area, and when they get into the adhesion area, they adhere to each other, and no relative slide occurs. And in the slip area, they can slide with each other. And if we see from the downward overview, so the contact patch is composed of the adhesion area in the front and the slip area in the back. In the slip area, the relative speed is greater than 0, and 0 in the adhesion area. So that's the tangential traction. And if we plot the creep and the creepage and the creep force into one figure, it's like this. So in the rolling sliding field, the creepage, the wheel and the adhesion area, adhesion slip distinction was there in the contact patch. But when full sliding occurs, the contact patch becomes fully sliding. And for the traction and the anti-slip control, their essence is to make use of the adhesion or the highest points in this figure to the best way, and avoid the large creepages or the full sliding stages, which is in the right part of this figure. Low adhesion. Adhesion is very important for traction and braking. But when the rail top was contaminated, the friction coefficient will reduce to very low level, as you can see here. And when this level is not sufficient to balance the traction or the braking, and the low adhesion problem occurs. And it can later cause train delay, signal pass, platform overrun, even collisions. And also the content surface damages, auto, large, micro, or full slip. And at the end, for example, the wheel flat is one example resulting from the low adhesion. And for low adhesion, over a long section is available from the viewpoint of anti-slip control. But for shorter ones, for example, just a few less than 1 meter or just a few meters, especially at high speed, it's not possible to control. And we developed and finite element model to simulate the wheel-rail transient contact at the short low adhesion area. And here we applied the constant torque and to simulate the wheel-rail rolling contact. And here we can see the results. Here is the low adhesion rung. It's only 40 centimeters long, and the friction coefficient is 0.03. And at the normal rungs, where the friction coefficient is 0.3. And in the low adhesion area, the friction force is not enough to balance the traction torque. So it leads because the friction force, the tangential content force was reduced because of the low adhesion rung. And imbalanced torque will result in the creepage increasement. And once the contact pads leaves the low adhesion rung, the accumulated creepage will lead to large content forces, as indicated in the by the red arrow. The content stresses the similar results. So in the low adhesion rung, the tangential force was reduced, but in the rung after the contact pad, after the low adhesion rung, the stress level was increased significantly. And here's the adhesion slip distinction. Before the low adhesion rung, the stable distinction was there, and once into the low adhesion rung, it becomes full slip area, and re-enter the normal rung. So the contact pad will change from the full sliding to again slip sliding. Because of this, it will also cause irregular wear. So the much lower wear in the lower adhesion area and the much higher wear at the end of the low adhesion rung, and also irregular plastic deformation. And if it's in the extreme condition, it will be flat. So that's a summary. The wheel-rail interaction is the key to the success of high-speed railways. Design of wheel-rail profiles is fundamentally important. Irregularity management is an important issue for high-speed railways. Adhesion management and the related control measures is a core problem for high-speed wheels. The wheel and the rail interaction in harmony is the ultimate goal for wheel-rail system management. That's all. Thank you for your attention.
Much, Dr. Zhao. Interesting presentation about the interaction between wheel and the railway. And for the following discussion, we have the moderator from Southwest Jiatong University, There is Professor Rong Chen. Professor Rong Chen is a professor and doctor supervisor in the Road and Railway Engineering Department and the Vice Dean of School of Civil Engineering in Southwest Jiaotong University. He has been engaged in the research field of urban rail transit, high-speed and heavy load rail structure and rail dynamics. So for the following session, I will hand over this session to Professor Rong Chen to guide the presentation. To Professor Rong Chen, the time is yours.
Hello everyone. Professor Rong Chen has has a break, so he just went out. So let's just start for the next presentation. Will be provided by Dr. Song Xiao, and let's welcome to Dr. Song Xiao.
Okay, thank you. Maybe I will give some brief introduction for our next speakers. It's Dr. Song Xiao. Dr. Song Xiao is Associate Professor and Master Supervisor, has been engaged in the research of multiphysics, multi-objective and multi-parameter optimization design, electromagnetic robust optimization, including sensitivity analysis, basic theory and application of maglev train, suspension technology and linear driving technology, the high-speed rail grounding system and pantograph catenary system, etc. At the same time, it is actively carrying out the application and innovation of artificial intelligence optimization design, combined with multiphysics coupling simulation in rail transit related fields. Won the honors of Special Expert of Sichuan Province 1000 Talents Program and postdoctorate of Jiangsu Province Double Entrepreneurship Program. As the backbone of young teachers in 2017, he won the first prize of the 8th Southwest Jiaotong University Teaching Competition for Young Staff. Up to now, 42 papers have been published in famous international journals and international conferences in the field of rail transit, and 25 national invention patents have been declared. So without further ado, please welcome Dr. Song Xiao with the topic of the development trend and prospect of the novel electrified rail transit. The time is yours.
Okay, I really appreciate for your introduction. Thank you. Today, the presentation of myself is titled as the development trend and prospect of the novel electrified rail transit. My name is Song Xiao, and my currently research area is electrified high-speed trains and maglev trains. Okay, so the presentation consists of 3 parts. The first part is overview of the development of electrified rail transit, and the second part is technology and industrial development strategy of high-speed maglev trains. And the final part is proposed development of high-speed maglev trains. Okay, from this figure, we can see the speed actually is internal thing of the times. Actually, you can see from the Stone Age, maybe we don't have the paths, and so normally when we traveled, we only by our own legs. So the speed of the Stone Age is roughly about 10 kilometers per hour. So when we went to the agriculture age, so maybe we have the horse, cow, or the camel. So these animals we feed it, and we took them as transportation tools, and the velocity of the transportation tools increased as the 60 kilometers per hour. And then when went to the first industrial revolution age and the second industrial revolution age. So from this trend we can see, so every industrial revolution, the ground traffic speed has roughly doubled, and fourth industrial revolution can reach about 1,000 kilometers per hour. So this is an overview of the development of the currently rail the transportation tools. Okay, from these figures, we can find the development of the integrated transport system is presented. So, so the horizontal axis is speed, and the vertical axis actually is so different transportation tools. So we can see from these figures, and maybe the waterway and the speed is comparatively low and only can reach about 40 to 60 kilometers per hour. So, and every day normally we drive, so the car can reach about 60 to 120, at least in China. The limited of the upper limited of the speed is about 120 for the highway. So the urban rail and is quite similar velocity with the highway. So the ordinary speed, high speed railway can reach about more than 300 kilometers per hour. So I think there is a gap between the high speed railway and the voyage. So normally airplane can the maximum velocity of the airplane can reach about more than 1,000 kilometers per hour. But there's no transportation tool between the velocity range between the high-speed railways velocity range and the airplane velocity range. So I think probably the high-speed magnetic trains can make up this gap, and we can see the high-speed magnetic transportation is a rail transit system which is driven by magnetic levitation and linear motor. The maximum speed can reach about 600 kilometers per hour, which makes up for the speed gap between the high-speed railway and the civil aviation. Okay, as we know, the relationship, there is three very critical relationships existing in the high-speed railway. So they are pattern graph catenary relationship, wheel rail relationship, and fluid solid coupling relationship, respectively. So as a unique power entrance for high-speed trains, the pattern graph catenary system is quite important, which it can achieve the high voltage power based on this system, and as a key for supporting train bodies and provide the electrical grounding path for the high-speed trains. The wheel rail system is also very important. Apart from these two, and fluid and solid relationship, which directly correlate with already aerodynamic performance of high-speed trains. So three of these relationships are very important for the trains. But from these figures, we can see the speed is internal theme of this time, and but the wheel rail relationships and the pattern graph catenary relationships sometimes restrict the continuously increasing of the operational speed of high-speed railway. So it's really hard to overcome this kind of technical bottlenecks, and such as pattern graph catenary relationships and the wheel rail relationships, especially under the high-speed condition. So as we know, the world record is created by the French companies, Alstom company. They designed the high-speed trains prototype can reach about 580 kilometers per hour. So that is the fastest high-speed trains until now. So, but if we want increase the operational velocity for the high-speed trains continuously, sometimes the pattern graph and the catenary relationships and the wheel rail relationships just give us a lot of restrictions. So we have to overcome these kind of technical bottlenecks. The second figure is actually the speed of high speed is operational velocity of trains with a ratio of the traction and the drags. So we can see along with the increasing velocity of high-speed trains, the basic resistance is also increased as well. And in the meantime, the traction capacity declines, and from the 100 kilometers per hour to 500 kilometers per hour, almost the traction capacity curve is we can see is very flat, and capacity can be viewed as a constant. So that's why we from these maps we can see actually there have been a lot of high-speed commercial line, and but I think the magnet, especially the high-speed magnet transportation, can also satisfy some of the city's requirements. So as we can, for example, like Beijing, and there's about three, big cities around Beijing, and if they're called the half-hour economic circle. So if we can apply this high-speed magnet transportation as how to say can compress the travel time between the within these half-hour economic circles. So this is actually the energy consumption and the emissions comparison between the high-speed trains and high-speed magnet trains. From this table, we can see from the aspect of energy consumptions, and we can see the high-speed magnet trains even performs better than the high-speed train for the carbon dioxide emissions. Also, the high-speed magnet trains, and have some its own advantages. So from these figures, and we can see because China has pledged to peak its carbon dioxide emissions around 2030. So I think as a very environment-friendly tools and very quiet tools, the high-speed magnet trains can be chosen as a very ideal transportation tool. Okay, this is currently situation of the development high-speed magnetic trains. So the first figure at the right-hand side, we can see this is a Japanese superconducting magnetic prototype, and this one has the commercialized central magnetic suspended line will be opened in 2027, and now the maximum of the test can reach about more than 600 kilometers per hour. So that is a very astonishing number. And the second photo is actually is a hyperloop. I think some of you have already known this kind of technique, because Hyperloop One actually is one of the sub companies of Elon Musk, so which is the owner of the Tesla company as well. So Hyperloop One actually just planned to build a commercial line between Dubai and Abu Dhabi and Dubai. So the total distance is more than 100 kilometers, and the speed can reach more than 120 kilometers per hour, because they use a technique to to maintain the condition in the tube as a vacuum condition. So there's very low air resistance for the trains, and they also use the magnetic levitation techniques. Okay, so if we want analyze the advantages of the high-speed train magnetic trains, we can see actually there's no mechanical contact. So that will result in very less maintenance of equipment, and even there's from these figures we can see definitely the magnetic trains have a lot of advantages. So and this is a turn and climb capability. So this is a comparison between the high-speed magnetic trains and the high-speed railways. We can see, especially for the turn radius, and we can find under the different speed of the different speed, and we can see the high-speed magnetic trains definitely performs better than the high-speed railway in terms of the turn radius. And for the aspect of the climb capability, we can see the high-speed magnetic trains sometimes can reach about more than 100 per thousand, and for the high-speed train only is 30 per thousand. So definitely in terms of the turn radius and the climb capability, in both of this direction, I think the high-speed magnetic trains performs better and than the high-speed railway. Okay, sometimes we also care about the noise and vibration, and especially the noise. I think that is the largest advantages for high-speed magnetic trains. So we can imagine if we want, to build a commercialized real high-speed railway in the city center. Sometimes we have to consider about the noise, and sometimes because along this railway and the people lived besides the railway, they also care about the noise, and because the noise is, if the level of noise is too high, and sometimes even will affect the price of the property along the railway. So noise is also the very important performance index we need to consider. For the electromagnetic radiation, that is most important, I think, performance index, and we have really do a very full investigation about the electromagnetic radiation at different locations, and we can see there's a different colorful bars, and blue, red, green, and purple, and these bars and means we detect the electromagnetic radiation at different locations. Sometimes it's in the train body, and then sometimes it's close to the train body and close to the electromagnets. And so this is the full figures. And TGV actually is the high-speed trains in Korea, and the TR-08 actually is a high-speed in China, the currently the most advanced type. And apart from the high speeds, I will also present the performance of the underground and high-speed magnetic trains in terms of the electromagnetic radiation. So from these figures, we find
5 more minutes, please.
Okay, thank you. So until now, there's several very classic magnetic techniques, and for example, this is the Japanese used superconductive and magnetic techniques, and this is magnetic traffic invented by the Americans, and they use the permanent magnets as the source of providing the levitation forces. And this is our achievements, actually get by the key laboratory in Southwest Jiaotong University, and they use high temperature conductive material as the source of providing magnetic suspension force. So my team is now focusing on the high-speed trains, which is driven by the electromagnets, and which because in Shanghai actually there's there's a commercial line between the airport and the city center, and so this high-speed magnetic trains techniques is actually at very beginning is achieved from the German. So actually now we based on this technique and we want to improve the previous prototype and increase the speed as well. And so now we have some basics and technical foundations, and because in 2015 and my team and me and participated in the project about the Changsha Changsha magnetic line, and which is a commercialized line and linked between the airport and the city center, and which the total distance is about more than 20 kilometers. So as we have the full experience of designing the medium and low speed magnetic trains, and we also have the technique about the designing the linear motor, which is very critical components for providing the horizontal thrust for the magnetic trains. And so we also have the techniques about the IGBT converter designs, and also produced the IGBT, this power electronics components itself. So we have also now we focusing on the project for the high-speed magnetic trains, because we always cooperate with German companies, and now we got some project from the Qingdao Shifang. Actually is a very key department of high-speed rail transit in China. So we cooperated with them and accompany with them and to design the critical components of the high-speed magnetic trains. Okay, thank you very much for your patience. Thank you.
Okay, thank you very much, Dr. Xiao. It's very interesting insight to the future of rail transit, especially in the maglev technology. So I can see that Professor Rong Chen already joined us in this forum. So I will give time to Professor Rong Chen to guide the final session today, and later on, please give some summary from our speakers from Southwest Jiatong University. The time is yours, Professor Rong Chen.
Okay, thank you very much, and it's my pleasure to attend this webinar. And now we will have the third speaker, Dr. Huailong Shi. He's an assistant professor in SWJTU, and his research interest includes railway locomotives and vehicle dynamics and control, railway vehicle design and reliability, long-term train dynamic performance test, lab test for vehicle components, safety monitoring system and software development, and huge data management system for high-speed train. Let's welcome Dr. Shi to give us the presentation. Thank you. 开始。
为什么？
卡住了吗？
Hello everyone. This is Huailong Shi from Southwest University, and I'm a lecturer at TPL. Today, my topic is about high-speed bogies and vehicle dynamics. It contains 3 parts, and I will start from the background. In China Railway, we have several models for various speed. From 160, 250, and 350 kilometers per hour. And we have classified high-speed train.
Excuse me, Dr. Shi?
Yes?
Your screen is still minimized. I mean, it's 10%. So please adjust it to 100% so that we can see it in the full screen.
Okay. A second. 他说大小不一样，它是最小化的，不是，
它是
屏幕。你先退出来，你是用屏幕。
你把它关了，整个关。
你先屏幕先取消，你现在没有共享。
你现在不是共享。
对，没有共享。
没有共享。你先退出嘛。
播放的。
退出来先共享。
你有2个屏幕，现在你的。你现在。
Okay, it's good now. You can continue.
Okay, you can see the full screen.
Yes, it's very good. You can continue.
Okay. For the next step, the China Railway is planning to operate high-speed train at 400 kilometers per hour. The topic is about the bogie. The car body is usually supported on 2 bogies on its 2 ends. So the bogie supports the car body and other key parts of a vehicle. It determines the speed, the safety, as well as the curve passing performance. Okay, so this is one diagram for the bogie in the CRH 380 Type A series has been train operated in Beijing to Shanghai high-speed rail line. This is a bogie with a traction motor and J-box. So it's a motor bogie. It will traction the vehicle to high speed. Another type bogie for the 380 Type B. Among them, I want to talk is the traction and braking system. So we can see the motor and J-box that connect by a flexible coupling to give the traction force and the braking force to the vehicle. So I will give an introduction about the bogie. A single wheel set can go over a curve, and a single wheel set can steer it itself on the track. But a bogie will assemble 2 wheel sets or more wheel sets together to support the car body. So the first function of a bogie is the support, then steering. And besides the steering, the curving performance is quite important for the vehicle to go over various curved tracks. It also has the ability to damp the vibration from the track excitations to the car body to give a good ride comfort for the passengers. So enough damping is located inside the bogie through some suspensions. Okay, we will see some of the components of a bogie. Usually, it has three mass components: the wheel side and the frame. Right, the frame is supported on two wheel sides through suspensions. The suspensions contains springs, rubbers, dampers in three directions. So the two suspension system and the frame make a bogie. Among the bogie, the various components are connected together or assembled together by the suspension elements. For different type high-speed bogie, the main components are similar, but they are arranged in different forms according to the design speed. For the frame, its main structure of a bogie, it assembles all the elements together to make it work as a subsystem to support the car body. This slide shows the wheel side. So two wheels are assembled to one solid axle together, making it rotate as one body. Among these components, the suspension system used to support the frame, used to steer the wheel side, used to brake and accelerate the wheel side, and transit the force from the wheel contact to the frame, then to the car body through the suspension system. Among the suspension system, usually for high-speed rail, two-level suspensions is enough to isolate the vibration from the track excitations to the car body. In the primary suspension system, it used to connect the wheel side to the bogie frame. In three directions, we see the yellow one, the steel spring used to support the frame, and the red one in the left bottom plot. The red one is called the swing arm. It's used to steer or get the wheel side to the frame. The pink one is the damper, right? A damper. So the damper at its two ends of a damper, it usually equipped with rubber joints. In the secondary suspension system, it's used to connect the frame to the car body. For a good ride comfort, it usually make it very soft. So it's equipped with air spring system. In the longitudinal direction, in order to control the hunting motion of a bogie, some two yaw dampers are equipped at one side of the bogie frame. For the longitudinal sleeving, it's used to transfer the traction or braking force between the bogie and to the car body. It's usually equipped with a large stiffness. To isolate the to damp the lateral vibration, so it is usually equipped lateral dampers between the frame and the car body. In some cross-wind case, in order to provide enough anti-roll stiffness, anti-roll bar system is used to provide the car body to roll over. This slide shows some detailed components of the secondary suspension system. Besides the ice-spring system, for some bogies, it uses a steel spring. The reason we use ice spring is because it solves support to the car body for a good ride quality. Besides that, it can keep the car body floor to a certain height from the real surface. So it can keep the car body floor in a right height in the platform for passenger to get on or get off. So with more load on the car body, the stiffness rises too. So the nonlinear performance of the spring is usually modeled in the simulation or tested lab to confirm its performance. For dampers allows redirections, right, to damp the vibration from the track excitation to the car body. So for different use, usually is in vertical and lateral direction. Another damper called yaw damper is to control the yaw motion between the bogie and the car body. The dampers usually is hydraulic one. Is output force is dependent on the excitation, frequency, displacement, as well as the damper. Next part I want to show is the vehicle dynamics. One serious problem is called the hunting motion. As another professor shows, a cone tried introduce a hunting motion. So how the hunting motion looks like, why should we avoid them to for high speed? The hunting motion will make the vehicle unstable in the lateral direction, will introduce large wheel side force on track. So it will introduce large vibration on the track and the vehicle. An index is called consistency to evaluate the geometric contact between the wheel and the rail. It's called the consistency. As the wheel side moves laterally, the equivalent consistency will change. So in some standard like USA 518, it will introduce an index called inerticity to judge this value. It determines the hunting speed of the vehicle. Usually the vehicle should be operated under this limit. And a large consistency is good for curve passing, but a large consistency will introduce severe hunting motion. So it conflicts between the running performance on tangent track and curve tracks. So we have to make some compromise. We have to select the suspension parameters to comprise the conflicts of the running behavior on tangent and curve tracks. To judge the equivalent consistency, the vehicle are designed to different running speed with assigned equivalent consistency. This table comes from an international standard in Europe for international standard of Europe. The hunting behavior, we can study it from a wheel side. For wheel side, the hunting amplitude, the hunting frequency can be determined from its geometry. The rolling radius, the lateral distance between the left and right contact point, as well as the equivalent consistency. So the frequency can be determined. But how it looks like for a bogie. In the bogie design, especially for the primary suspension, for some type of bogies, it uses a large stiffness in the primary suspension. We call that radius steering bogie. And for this type, the hunting frequency, the angular frequency is written like this one, and we can get the wave length with it. So it's determined by the equilibrium constantly as well, and its geometry, the wheelbase, right? But for a flexible steering boogie, it means the steering stiffness between the wheel side and the boogie frame use the soft spring. And for this type of flexible spring boogie, we don't have a analytical form of the hunting frequency and wheel form. We have to get it by numerical solutions. Besides the wheel side, we can see, besides the hunting motion of boogie, we see some other suspension modes of a boogie: the bouncing, the roll, the pitching, the sway, and the yaw motion. The yaw motion is much look like the hunting motion. In case of hunting, the boogie experience yaw motion and sway motion usually. This is some numerical results to get the hunting frequency for wheel set, for flexible steering boogie, then for rigid steering boogie in different speed. First, we see that the frequency is almost linearly dependent on the quantity, then the vehicle speed, right? We have various scores of track. In China is 1435 millimeter, but in Europe it has 1520 millimeter. But the hunting frequency looks same on different track system. Besides the boogie hunting, how the car body vibrates. So this simulated plot to show how the car body vibrate during hunting. This second dimensional diagram show how the hunting move. The car body, the blue one, it yaw, right? It experiences yaw motion and swing motion. For the swing motion, it had two taps. It is a coupled vibration between the rollover motion and the lateral motions. So this is the hunting. This video, we recorded a video about hunting motion. For a traditional railway system, we put a camera on the boogie frame one to record this hunting motion. So this abnormal case, since we can see that the wheel flange connect to the rail side. It had some potential risk of derailment. Besides, in order to evaluate this kind of abnormal vibration, we have to do some field measurements. The hunting motion, we also introduce abnormal vibration on the car body. It will make the ride comfort reduce a lot. For the left plot, it's ICE3 has been tuned. You can see that the car body sway a lot at a low frequency, about 1 to 2 hertz. Another plot on the right, we recorded in China for the has-been train. It's shaking, right? Car body is shaking at 8 to 9 hertz. It will also deteriorate the ride comfort. So the hunting motion, all these two types abnormal vibration on the car body is caused by the hunting motion of the boogie. So how to evaluate the hunting motion? It's usually named the celebrity evaluation. This slide shows how to the simulation. Usually we can evaluate the lateral vibrating amplitude of the wheel side. If it if it reaches the view real clearance, then a flange contact occurs. So this is called unstable. So numerical simulations to different speed to see how the vibration reach the limit. So the speed is called critical speed, right? Called critical speed. That's the highest speed the vehicle can be operated. On the test bench, in the state attraction lab, we have a full-scale roller rig. The roller can rotate up to 6 kilometers per hour to simulate the running speed of the vehicle. And the roller can vibrate in 3 directions. So in order to get the maximum running speed, usually it uses some constant speed excitation method or coast down method to get the speed. The first one, the linear critical speed, pure rolling case or constant speed is performed on the roller rig and increasing the speed slowly until unstable motion is founded on the vehicle. Usually the vehicle, the roller rig can put some track irregularities, so to see how the vehicle behave in different track excitation cases. So this is how we did it on a test bench. About how to evaluate the harness stability on track, we have to put some accelerometers on the frame end, like the upper right plot. Accelerometer is plotted on the frame end to measure the lateral vibration. Usually it's acceleration. So according to the international standard from European, USA, also the third one in China, we used to evaluate the hunting stability of the vehicle. So for the amplitude as well as its RMS value. So another method is the wheel side lateral force. If we can get the wheel real contact force, we can also use this index to judge the stability of the vehicle. Okay, I think that's all I want to share with you today. And if you get any questions, we can talk it later.
Okay.
我就介绍这么多。
Okay, thank you very much, Mr. Xi, for the final presentation. It's very interesting to see the test facility in China. You can see the full car body testing of the high-speed train. So moving on to the next agenda, we will have a panel discussion. The panel discussion is between the speakers. So I would like to invite again all the speakers from Indonesia as well, Mr. Najab, Mr. Rusli, and also Mr. Waru to join us in this discussion. Okay. Is everyone join the discussion now? Okay, perhaps I will start by Mr. Najab regarding the propulsion laboratory in BPPT. So I would like you to elaborate more on the future cooperation and collaboration, maybe to improve the facility in BPPT. And later on, we would like to ask the discussion also from the SWJU side about the test facility. Okay, I give you 5 minutes, Mr. Najab. to discuss more about the propulsion laboratory.
Okay, maybe first I would like to answer the two questions from Mr. Lukman, I think, and from Humas PTSPT, I don't know the name. Yeah, the question is about how the two IEC standard you mentioned, are they both mandatory or can adopt only one of them? Yeah, and what modification in your laboratory in order to test traction motor for high-speed train? These are two questions. Maybe I would like to share a little bit. Yeah, yeah, we need both standard. Yeah, sorry. Because the first standard IEC 60349 tests traction motor only on a standalone situation. It's categorized as component testing. If you are electrical motor manufacturer, you need this standard. So the standards mainly maybe for manufacturer of the electrical motors. So the other standards, IEC 61377 is a traction system, not only traction motors it tests, but also the whole traction system with test cycle close to real operation. For a trade manufacturer like Inca need this standard, I think, yeah, in my opinion. So as stated in the standard 61377, the traction system under test incorporate at least one complete traction conversion line. Also, yeah, one transformer in the case of IC supply or input filter in the case of DC supply. The representativeness of the traction system under test versus the actual traction system is agreed between user and the manufacturer. So this is the difference, yeah, between the two standards. I think before we test using IEC 61377, so the electric, so motor traction should be passed the first standard, yeah, 60349. Okay, so sorry, I want to proceed to the next. Yeah, also both standard has a close relation actually. So as said in section 4, the standard 61377, reference temperature of the motors, winding or magnet shall be according to values as in IEC 60349 series, yeah, or subject to agreement. So also in the for hot condition when the starter winding temperature are equal to the reference temperature in the IEC 60349 series, yeah. So these two standards is very close, yeah. So, but the as I said before, that maybe IEC 60349 is for electrical motor manufacturer, but 61377 is for a train manufacturer. Yeah? When we want to test traction system, the whole system, so we use 61377. So that's my answer.
Excuse me, Mr. Najab. Yep. Do you have any question to our speakers from Southwest Jateng University?
Okay. Yeah. Development of high-speed technology, train technology in China is very amazing in the last decade. So I believe SWGU plays key role in this amazing development. So we hope, yeah, when I visited Chengdu in 2 years ago, yeah, almost, Southwest Jiaotong University has numerous facilities regarding development, high-speed train, and so various laboratories for HST when I visited Chengdu. Yeah. So BPPT can learn much from SWGU, how to gain knowledge in HST technology. Maybe I hope Southwest Jiaotong University can guide us to develop such facilities, such as propulsion laboratory or other laboratory. That's my hope, at least. Right, that's it.
Okay, from Southwest Jateng University, do you have some comments on Mr. Najab's question regarding the possibility to implement a test bed of the high-speed train in Indonesia?
那么各位老师就直接回答问题吧，赵老师，你把赵老师的那个 PPT 放出来。
你说他们想去轻动力相关学习，
对，那个是国家重点实验室。他们想去。他们就说了要来成都学习一下。你说你这边经验表。对，就给他们回复一下，就是欢迎他们到时候来交流学习。
好，gentlemen, it's a very good day. It's very we learned a lot from this communication today, and we're also happy to hear a lot of questions from your side. And later on, we will reply all the questions one by one. And before answering the questions, I would like to say you are all welcome to come to our lab and to visit us and to conduct more thorough critical communications. And wish you can do this trip in the near future. Okay, thank you. And now we would like to we collected some questions from your side, and we would like to answer them one by one now. And first question is
excuse me, for the question and answer, we will proceed after this session. So for this session is between the speakers only. So if the speakers on both sides, yeah, we have question. The time is now.
For this, I think the high-speed railways is quite a challenge for Indonesia, and especially thinking of the environment conditions there. In the rains, the more damp, and so today I mentioned the low adhesion problem. So it's also from this point of view, and we in the rainforest areas there must be a lot of chances for low adhesion problems, and we do think that's a very important issue. Need further investigations from both simulations, field observations and measurements, and also from trial tests, maybe on the once the track is ready. So I don't know if you side have already collected some information about the low adhesion problems from the high-speed railway, which is under construction now in Indonesia.
Okay, thank you, Dr. Xiao. I would probably ask to Mr. Rusli related this matter. Dr. Xiao mentioned about the environmental challenges in Indonesia. So, do you have any study or experiment about this matter? And please, you can elaborate about that topic again. Please, okay. Dr. Rusli.
Thank you, Mr. Dr. John. Yeah. Actually, thank you very much for the question. Actually, in Indonesia, high-speed train is not available until now. So that's then just only I think that's because the Indonesia environment is very narrow and the high rate of rainfall, and then the reliability is high. I think it needs an additive control. But until now, I didn't do it because just I only do with the slow speed. So I think for high speed, I don't. I have no idea for that. Okay, for high speed train, maybe from this we can collaborate it between us so that we can discuss about it. We can discuss about it. And then because from the paper actually anti-slip controller actually has done, but for slow speed for the original for slow speed train, but for high speed train I don't know exactly. Okay, this is all for me or for this equation. But I think this is important for us in Indonesia. If we want to implement the high speed train, I think we have to care about the readaptive control. And can I get a question?
I beg your pardon. Could you please repeat your question?
Oh, okay. Yeah, okay. As you said that in high-speed train, this is not possible to control the sliding on the adhesive control for long line. Is correct? Right?
Yes, we have control the systems. Yeah, for both actions and anti-slip.
Okay. Even though we can make the mathematical model of the hill and rail, it's not possible to make an advanced control technology. Hello? Hello?
From China, can you hear the question from Mr. Rusli?
The audio is not very good, yeah, Mr. Rusli. I don't know.
Oh, yeah.
With the microphone, Pak Rusli.
Hello?
Sorry, we didn't understand the question very well.
Hello? Yes. You can hear me?
Yes. Yeah. Please proceed, Pak Rusli.
I'm sorry. I don't know what happened there. Hello?
Yes, Pak Rusli, please carry on.
Okay, Pak Rusli, please proceed.
You can hear me?
Yeah,
yes, I can.
We can hear you, but with a very strong echo.
Okay.
Yeah.
Yes. I can repeat my question. Hello? Hello?
Yes, please.
Hello.
Pak Rusli, please continue.
Yes, we are listening.
I would like to repeat my question.
Yes.
Okay. You said that it is not possible to control adhesive control for long line in high speed train. Is it right?
Is it possible to what?
For long line, control the adhesive control for long line, because
you mean the control for the long low adhesion areas?
Yeah, it's not possible.
Yeah, it is possible. It is possible.
Okay.
Yeah, it is possible. It means the threshold for the so you for the control system, the threshold is about 17% creepage. So which means it's already maybe tens of meters, even longer than hundreds of meters, low adhesion areas. But in reality, I think may not be so long. There are a lot of short low adhesion runs, and these runs may not long enough to trigger the anti-slip control system, but do cause the large slip, the large wear and the large rolling component fatigue problems. So that's the concerns we are dealing with. But it's very difficult to do this to control the short low adhesion runs, because the time period is very short. You need to collect information and calculate and get your response, and then to operate through the mechanical structures. And the whole process needs some time, and this time it also needs a very large accuracy. And so at this moment it's very difficult, and I don't think there is such control measures in over the world.
Okay, thank you. I hope that's answered Mr. Rusli's question, and I will give the opportunity to Pak Waru for asking some question to our colleague. Maybe short question, 2 minutes, Pak Waru, please.
Okay, thank you. But I think I don't have any question related to my expertise, because my expertise is power electronic. The material presented by the China side is not about the power electronics. It's about the mechanical system and the relay system. I think I do not have any questions regarding the railway system. Thank you very much.
Okay, very well. So I guess we can close the panel session for this webinar, and then we will move on to the question and answer. We already have some list from the Zoom chat column and also from YouTube, and I will read one by one for the question, and we hope the speakers can provide the answer. So the first question, from Mr. Lukman from BPPT. I think the topics of Mr. Shinzao and previously Mr. Rusli are complement to each other. To Mr. Rusli, how do you think the effect of wheel rail profile to your control algorithm? And to Mr. Zhu, given a specific wheel rail profile, how do you control or manage the anti-slip or adhesion management? So please, maybe first to Mr. Rusli, please answer.
Okay, thank you very much for Mr. Lukman. Just as I gave in the slide, actually from the paper, the control anti-slip can be solved by the disturbance observer with considering the dynamic of bogie. But in this paper is not care about the variation of parameters. So that I think because in high-speed train, the vibration of train is very high, and harmonic also. And then the both harmonic, resonant, and vibration can influence the parameters of the parameter of traction motor. So that for the design, the control anti-slip should be or have to care about it, the harmonic, resonance, and vibration, because in high speed is very high. But in Mr. Choi from Chinese, we can just control only for short line, cannot long line. This is, I think, it is better if we can measure within short time, measure, and then with the sensor less, because the sensor have sometimes slow resolution. If we measure variable with the sensor, maybe takes a long time. So that's for high-speed train. This is not enough for keep decision with the sensor. I think first we have to make sensor-less vector control, and then the algorithm should be care harmonic, resonance, and what is vibration, and then the sampling measurement should be so short as possible. Okay, because the high-speed train is the variation of parameters very high. Okay, that's it for me.
Okay, thank you, Mr. Rusli. And for Mr. Zhao, could you please answer the question?
Yeah, if I understand the question correctly, so the audience want to know if the real profiles can influence the control algorithm for the anti-slip. For this question, I think it is yes. The real profiles is the most important characteristic of a real system. Of course, indeed, influence the real behaviors and further influencing the control algorithm. But this influence will not be large. Will not be large in most cases, especially for high-speed rails, where most of the tracks are large radius curves or tangent tracks. So the influence will be very limited. This is answer one. And answer two is this influence might not be really important for the actual control system, because the actual control system based on the actual measurement. And the measurement based on we basically measure the rolling speed, the forward speed, and determine the creepage a bit from them. So its influence was included by the system. So we just measure it. It doesn't matter it has influence or not. So from this aspect of so from the engineering point of view, it doesn't matter which the profile is that. So that's my answer. I hope the audience is satisfied.
Okay, I hope Pak Lukman still on the Zoom and have the answer from Dr. Zhao. And we also have a question again to Dr. Zhao. It's from Mr. Miming. How do you set up the baseline or the highest irregularities that could be accepted? What kind of tools do you use? If you use accelerometer, how much acceleration accepted regarding to safety issue?
Yeah, this is a very good question, and it's also directly related to the daily operation. For this question, I have to say first, to determine such a limit for the irregularities. It's not easy, because such a limit you could determine from the aspect of dynamic virial counter forces. For example, in China, we think 170 kilonewton should not be overloaded, shouldn't be passed. So if you apply this dynamic constant force, you can determine a limit for the irregularity. But you can also perform to determine a limit from the aspects of such as noise inside the train, and also the vibrations from the vibrations at the actual box. But the difficulty is there is no well accepted principles for all these methods. So, for example, the 170 kilonewton is the empirical recommendation. So it's hard to find out scientific basis for this method. But in operation, we do have some limits which were determined, which were mostly from experience in the past and from industrial experience. And some of them have been approved by the recent studies. So my answer is basically there's no simple answer to this question, and we can do it from different aspects, and every aspect has a lot of uncertainties, and a lot of research are required. Thank you.
Okay, thank you, Dr. Zhao. I hope it's answered. And now we have a question. This is from Mr. Febri from PT Inka. PT Inka is the railway manufacturer of Indonesia. It's a question to Pak Waru. So as I see, inverter is an emerging technology right now. So is it possible to apply this kind of inverter to high-speed train? And also question to our colleagues in Southwest Jateng. Do you have any experience to apply this kind of inverter to high-speed train in China? So the first question for Pak Waru, please, Pak Waru.
Thank you for the question from Mr. Febri, if I do not mistake. Okay. Actually, I can say the inverter technology we're mastering today will be able to implement it in the high-speed train application. Especially if we implemented the inverter using the high-speed switching devices, just like the SiC or silicon carbide based device, which has I presented before. In the high-speed train application, the motor, the traction motor, rotates in the very high-speed rotation. So we need an inverter with high-frequency switching, and the switching component available commercially today, which based on the silicon technology. The popular one is the silicon IGBT. module. Most silicon IGBT module has a switching frequency only in order 1 kilohertz until 5 kilohertz, not higher than that. But using the silicon carbide technology, we can achieve the higher speed switching until theoretically until 100 kilohertz. So we can drive the high-speed train motor, traction motor, using this technology. So that's why I will focus on the SiC-based switching devices for developing the converter on inverter to drive the traction motor, especially for the high-speed train. Okay, I think that's my answer for Mr. February question. Thank you.
Okay, thank you, Pak Waru. And from Southwest Jateng, do you have any comment on this question? It's about the SiC inverter application in high-speed train in China. Do you have any experience on that matter?
Sorry, the teacher who was the presenter who was making the presentation on the electrical engineer, and he's not here anymore because
okay.
So we cannot answer this question. Sorry.
Okay, I see. We will proceed the list of questions to you maybe to answer later.
Yeah.
Okay. Moving on to the next question. It's from Mr. Yunendar. Mr. Yunendar is the lecturer from the ITB. It's the Institute of Technology, Bandung. It's a question to Dr. Xin Xiao. The first one is, how much sensitive are the wheel and rail profiles to the rolling contact fatigue and other surface damage of wheel and rail? Is it worth to optimize the wheel and rail profile in order to minimize possibility of rolling contact fatigue? And the second is, rolling contact fatigue has a potential to occur on the high-speed operation with relatively lightweight vehicle. What about on the freight wagon operation, which operates at low speed but on the very high load? Does rolling contact fatigue also occur on this condition? And what is the difference between the damage phenomenon on the wheel and rail surfaces of low speed but heavyweight wagon compared to high speed operation with relatively lightweight? Do you have any example?
Okay. This question, first question one. It's indeed, we do have solved a lot of rolling contact fatigue problems by optimizing the wheel rail profiles. So the answer is, the simple answer is yes. It is possible to it's worth to optimizing the wheel rail profiles in order to minimize the rolling contact fatigue. And how much sensitivity? It is indeed very sensitivity, as I presented during my presentation, simply because the profile optimization we have done up to now is normally less than so the variation we did is normally less than 1 millimeter. So very small modification on the profiles can result in very different consequences. So if you are 1 millimeter thicker, for example, the flange, you will got rolling contact fatigue problems. and it's just maybe half millimeter less, no problem will occur. So this is the answer to this question. And the other one, the second, the rolling content fatigue is it's not really a problem for high-speed trains, because most high-speed trains mostly runs on large radius curves and tangent tracks, where the real interaction is quite good. For the lower speed trains, and also for the even the heavy the freight trains, the problem might be mostly are worse, because these trains normally passes sharp curves and also with the large slopes, and this will worsen the wheel-real interaction and stimulate the occurrence of rolling content fatigue. They are different, but it's hard to. I mean, I didn't say there's no rolling content fatigue on high speed. It's just less severe and less occurrence rate. But if let me to, but it's hard to classify them. So for the rolling content on the high speed and on the low speed or the heavy wagon trains, but we can roughly say for the high speed trains, because of the low weight, the rolling content fatigue is more determined by the tangential contact or determined by the friction force. And for the wagon, or especially the heavy haul train railways, the problems become more complicated, because the vertical load and the friction force can both contribute to the rolling content fatigue significantly. But for more detailed characteristics, it's rather difficult to give a short introduction here. If this audience is very interested in this topic, he can contact me, and I can send him some publications we have made in the past. Thank you.
Okay, thank you very much for the answer. I have a notice from our colleague that there is another agenda, so I think we should finish the question and answer session by now. We would like to say thank you very much for all the speakers and all the participants for joining us until finish today. And for the next question, which not yet to be answered, we will send it by email to all the speakers, and I hope they will give the answer by email. And I would like to say thank you, and also apologize if during guiding this webinar I have some mistakes and some inappropriate manner. So I will give back the forum to Ms. Lita for the closing remark. Please, Ms. Lita, time is yours.
Thank you, Mr. Benny. We are at the end of today's webinar. Thank you for all the speakers, moderator, and audience for presentation and discussion. We hope that today's webinar will benefit all of us. For the audience, don't forget to fill the attendance form, and the presentation material can be downloaded from the link provided in the chat room. We will update the link with all the materials from the presentation. Yeah, then if you have any further question regarding this webinar or next webinar, you can follow social media of PTSPT, BPPT. You can find it in Instagram. So thank you very much for joining us today. We apologize if there's mistake in this webinar. See you again in the next event. Thank you. Bye. Bye. Thank you, Zhang.
So can we leave now? Yeah.
Yeah.
Thank you very much.
Okay, thank you.
Bye.
Thank you very much.
Thank you.
For all.
Bye bye.
Take
Thank
care.
you.
Bye.
Thank you all.
Bye.
Thank you for your.
And thank you, Lita. Thank you for the excellent
next.
from PPT.
Bye bye.
See you soon next time.
Bye.
See you next
Bye-bye.
time.
See you next time.
Masih no, 3, 2, 1, close it.
关上就可以了。
Close.
辛苦各位老师了。